Hello everyone, welcome to this video. In this video we'll be solving this question which states that prove that for each A in G we have some group G here, right? From this group G we take some element A, right? And then we calculate what is the centralizer of A. By centralizer, what do you mean? Centralizer of A means all those elements from this group G such that they commute with this element, right? So we are looking for those elements. Obviously A commutes with itself, so we are looking for a set within G such that this set, this is C of A, correct? So this centralizer becomes a subgroup of G. We need to prove this thing. So here, in order to prove that centralizer of A is a subgroup of G, we will be using two-step subgroup test. Right? What is this two-step subgroup test? First of all, we take any two elements from it and prove that the product is also present within this element, and then we take any other third element from this centralizer of A and prove that its inverse is also present within this same set. Then it would become the subgroup of G. So for that, we first of all prove that it is non-empty, right? So that means it should contain at least one element within it, and definitely that element is identity element. Why? Because the identity element, you know, commutes with all the elements of the group G, right? This is there for all G, right? So therefore it would surely commute with A as well, right? If it commutes with A, so therefore E is definitely present in the centralizer, hence this is non-empty. Now let's move forward in order to apply this two-step subgroup test. For that, we take two elements B and C from the centralizer of A. Then if B is present in the centralizer, by the definition BA would be equal to AB, and if C is present in the centralizer, then by definition CA would be equal to AC, correct? So in order to prove that their product BC is also present in the centralizer, we have to show that BC into A is equal to A into BC. That means BC also commutes with A. So what we do, we take this left hand side and then simplify it. So BCA, by the associative property, you can shift the brackets here, and you know what is CA? CA is equal to AC. So instead of CA, you can write AC. Again, you can make use of associativity to shift the brackets. So now you know what is your BA. Your BA is equal to AB. So you can write AB here, and you can again make use of associativity to have this thing. So from here you see BC of A is equal to A of BC. Hence we have the commutative property present with us. So this is the first part of the two-step subgroup test. Now for the second part, we take some element D from the centralizer of A and prove that its inverse is also present in the centralizer. So if D is present in the centralizer of A, it means that DA is equal to AD, right? And we wanted to prove that D inverse A is equal to AD inverse. So what we can do, we can post and pre-multiply this equation with D inverse, so that on this equation you have D inverse here, D inverse here, D inverse here, and D inverse here, so that you would have D inverse GA, D inverse is equal to D inverse AD, D inverse. So you see this and this combined, and this and this combined together, correct? You can write it like this with the help of associative property. And similarly, now you know, because D is some element of the group G, right? Because it is present in the centralizer, it means definitely it is present in our group. So therefore the inverse of the same element would give you the identity element, and D inverse would also give you identity. Hence we have identity here and we have identity here. Now E into A is again A, and A into E is again A, correct? So from here you obtain this relation that A and D inverse, they commute with each other. If they commute with each other, hence D inverse would be definitely present in the centralizer of A whenever we have D present in the centralizer of A. Therefore we can conclude that this CA is a subgroup of the group G, right? So I hope you understood this proof well. Well, that is it for this video. Thank you for watching.